Okay, good morning everybody.
Good morning.
And, welcome to the Geo-Python course. How's the volume on this microphone? Is it?
Quite loud.
Yeah, it seems quite loud even up here.
What about this one? That's okay, cool.
Maybe, is that better like that? Just, if I move it away from my mouth a bit. Okay, so yeah, welcome. We're gonna, I guess, get started with a little bit of practical information about the course. Glad to see that many of you made it here, and many of you made it here at 9 o'clock. Some of you I know came at 8 o'clock, and sorry about that if there was a miscommunication. But you've had a second here to look at what we're going to talk about today, and well, maybe now's a good time to talk about who we are. So my name is Dave. I'm the instructor. I guess it's listed for the Geo-Python course. And for this first period, well, I kind of teach it along with Henrique, who could maybe.
Yeah. So, well, can you hear? No. Maybe
Well, that's Henrique.
Yeah.
So, while he struggles with the microphone, you can see his name here. He's the one who's the instructor for the Automating GIS Processes course. So there's, you know, if you're kind of wondering what's going on here and don't know, we meet with these two courses in the same classroom during period one. So for those of you who are continuing on to thinking about taking this Introduction to Quantitative Geology course, we've split this now so that Geo-Python is the course for the geology students that you would generally sign up for, or anyone who only wants to take the course in period one. Most of the geography students would sign up for this.
Yeah. So in geography, for this year, it's a bit maybe confusing. So actually, we are kind of all the GIS is in total 10 credit points. So for the first period, which is basically this Geo-Python part, so if you cannot continue into the second period, you will still basically get 5 credit points from this one. But it will show us all the GIS, and then in the kind of extra information there will be a note that it was the kind of basics of Python part. So yeah.
So if you're confused about how any of this works, well, there's the two of us, and then there are 4 course assistants, and we are all happy to help explain the somewhat messy registration for the course. So for the assistants, Vuokko is here in the front. I guess at least some of you in geography would know who she is. And then Lotta is somewhere in the back. So she's the assistant for the Geo-Python course, and will be the same assistant for the Introduction to Quantitative Geology. And then you guys have 2 other assistants.
Then we have you can stand up then. And then do we have Hertta somewhere?
You'll meet Hertta tomorrow.
Yeah.
That session.
Yeah. So we will meet her. Yeah.
So that's the crew, and this is also a useful slide because these are the websites for the course. So we don't do anything in Moodle for this course. We don't post any other course materials in any of the university systems. We do our own thing here. And so geopython.github.io will be the course website for the first period, and basically everything you need for the course will be either on that page or linked from that page. So when in doubt, go there and look, and then contact us if you're confused about something. For period 2, we will have separate websites. It's not really that relevant for you now unless you want to look ahead to see what's coming.
Yeah, so basically if you click on those links, you will go to the materials from last year, and that's what's happened.
Yeah, the Geo-Python course is current, but the other 2 are still from last year. In terms of the meetings, obviously you found your way here. We're going to meet here on Wednesdays from 9 to 12 during period 1. And there are then these work sessions that they're optional, but many people end up finding them quite useful. And so there's one on Thursday and there's one on Friday. You can register for either of them, and it doesn't matter which one you go to week. As far as I know, there's not really been an issue of having way too many people there. Sometimes it's been pretty busy.
Towards the end of the course.
Yeah. Yeah, the last few weeks get a little bit more challenging with the exercises, and but anyway, if you signed up for the one on Friday, you can still go to Thursdays sometimes. If you signed up for the one on Thursday, you can go on Fridays. It's flexible, and these are optional. If you don't feel like you need to go because you're already a programming wizard, I don't know why you're here, but you know, you don't need to go to them at all. And yeah, anything else about AutoGIS? I left one slide blank because I didn't know if you had any other special.
Yeah, not at this point.
Okay. So, our next thing is to find out a little bit about who you are. We unfortunately don't have time to go through and like meet each person individually with this size of a group, but we'll do this greeting digitally, I suppose, and ask you if you've got a computer or a phone to go to this address. It's geo-python.github.io/poll, and if you go there, it will take you to a page that looks like,
If you just
let's see, it looks like,
Yeah, like that.
well, looks something like this. You have options that you can vote for this first question about which course you've enrolled in. This is just the kind of real-time response for those who've enrolled.
So the geographer seems to be a bit more morning people here. Although you have two options there for you.
Yeah.
other questions good for this point. Yeah, and maybe we can choose. Go through this, and maybe the one after that we can do as well.
Okay, so, you know, we're getting a sense here that there's something like 20 people in the Geo-Python or Geo-Python Introduction to Quantitative Geology, 23 in Automating GIS. There's more of you than that here, but that's pretty close to a representative sample. And so it's about half and half. And for this part of the course, that's actually kind of a nice thing because you can mix up and work together with people who you maybe don't work with that often, and many of you are probably going to be going through the same kind of experience, whether your background is in geology or geography. In learning to program, that kind of component is maybe not so important as your willingness to jump in and try to learn some Python.
Yeah. Let's take another question still. So basically we are also interested, like, why are you here? So I set up another question here. So basically, what types of things would you like to learn in this course? So if you can still answer that one.
And I think for this question you can select as many options as you like. So
yeah, exactly.
Programming with Python is a kind of obvious leader.
Yeah. Yeah, I'm happy if we get that one. Cool. I'm happy to see also skills related to reproducible research. That's definitely something what we are aiming at with the whole course.
Yeah. Yeah, so I think, you know, everyone seems to have gotten the message that one of the main purposes of the course is to learn how to program, basic programming in Python. And, you know, along with that, we will try to share lessons that are useful related to things like reproducible research. If you start to learn how to program and you get taught how to program like most computer scientists do, a big thing for computer science is reusing any code that you write and making the code easy to reuse, which directly kind of links to making things reproducible for your research. So if you're doing a master's thesis or even thinking of, possibly using Python for your bachelor's thesis, just being able to have a functional piece of code that produces some plot, and then if someone ever says, hey, how did you make the plot in your bachelor's thesis? I read it and it was just amazing. You can easily refer them to this code and say, yeah, you can go ahead and run the code and you'll reproduce the results. And it's really an area within the broader kind of scientific community that's being emphasized for all of us. Open science and reproducible research is something that's certainly a point of emphasis at this university and many other research institutions in Europe, especially.
Yeah, it's also a fact, like if you, any one of you plan to kind of go ahead with research sites, so now more and more journals, if you plan to kind of submit an article, so they are actually demanding for you to share all the codes and data that you have used to produce the results.
We have maybe one more question that would be good to do now.
Yeah, let's do one more. So now we know a bit of motivation for you guys, but what about the experience? So I'm sure that there are someone who has some programming experience, so if you have some experience, just point it out. Maybe while kind of seeing the results coming, so one of the motivation for actually Dave and I to originally develop this course as we have done it is kind of in terms of comparing for you to take the similar course in computer science, is the fact that the approach for actually learning stuff is quite a bit different, because we try to use such concepts that most of you are, I guess, geo people, so you're either geographers or geologists. So we kind of try to use examples that are familiar to you and easy to kind of understand. Whereas in computer science, the kind of problems that we are solving with programming are quite a bit different.
Yeah, I think the other thing is we're not really going to tell you much about what happens inside a computer. We won't talk about how numbers are represented in memory in computers and many of these things that computer scientists take as like really fundamental parts. We're going to be more driven by what we want to do scientifically and the types of data that you're likely to be using and things of that nature. So this is pretty good. I think this is quite similar to last year's group. There are a number of people who have no experience at all, and there are some who have a little bit, but maybe don't use that little bit of programming experience that they have. And we don't assume that you have any programming experience. So for those of you who are regularly writing your own programs, you might find that what you're asked to do in the beginning of the course is not necessarily that challenging. But you could also think about that as an opportunity if you have a friend who doesn't have any programming experience in the course, or see somebody, you could possibly share some of your experience and knowledge with the other people. I think it's great when the students in the course kind of work and learn from one another, like you often do. So yeah, we got one more question here about the programming languages. So that's a useful thing for us to see. Hey, there's a Fortran programmer.
Oh, that's good. Also quite similar as last year, so we have a lot of R users, some JavaScript, and some Python as well.
Okay, yeah. R is leading the way in Java, okay.
Yeah. Actually, although I don't really like the battle between R and Python, but somehow being a Python user, so now like for the first time, Python is actually more popular than R for doing data science, which is maybe, well, I don't know what it tells, but that's how it is.
Okay, so I think that's the kind of end of us getting some information about you for right now. And yeah, let's go back here. Now that we know a little bit of who you folks are, we'll try to get to know you a little bit better as the course goes on. But we can talk a little bit about the goals of this part of the course, or the Geo-Python part of the course. And essentially what we want to do is introduce, first off, the language Python and help you to learn some basic programming skills as part of your introduction to the Python language. Most of you who have some experience with programming in other languages will have some of these skills and be familiar with certain concepts that are common to all programming languages, but maybe don't know how to do these things in Python. So hopefully everyone finds some good things that they can take away. And the third point here is something that we're going to work on as we go along, trying to share with you some good practices from programming. And this comes really from I guess there's a number of different resources where we've absorbed some of these good programming practices, but a big part of it comes from the fact that computer scientists tend to look at what we do as natural scientists or even social scientists and sort of shake their heads, because they've come up with ways to write their software, to test their software, to make sure that it works regularly and the way it should, and development practices that we basically just don't use in the natural sciences, or seldom use. And it's things that would make us a lot more, well, I don't know if smarter is the right word, but these are things that make our little programs that we write to do simple things much easier to reuse, and tips that make it so that, like, as you keep adjusting your little program over time, that you can always go back and reproduce things that you've produced in the past. So it may not be that relevant to you right now, but as you go on and write master's thesis or something, if you're using Python, you will see that the first little piece of code you write will not be, you write your code and then that's it, I'm done with my master's thesis. You'll be updating it probably quite a bit during that process. So then let's jump now to some motivation for the course. If you're not already motivated, we're going to motivate you more, or at least attempt. Here's the course webpage. If you haven't been there already, this is just what it looks like when you come there, and I'm going to go to this lesson 1, motivation for the course. It's pretty big on the screen, so maybe you can see it there, but if you want to follow along on your own computer, you can do that as well. So this motivation essentially is something that's driven by data in this case, and as we've already mentioned, we have these goals to try to introduce the basic programming concepts in Python, to help you write programs that are easy to understand, that are easy to share with other people, so that if you do something and want to share it with somebody else, you have written your code in a way such that someone else could possibly be able to read it. So we'll give you some tips about how to do that. And other things like keeping track of the changes you've made to your code. There are simple ways to do that, and some of these other, like, reproducible science concepts that we've already mentioned. But for the motivation part, I want to kind of start by saying something about data visualization. And one of the things that we're going to talk about in the course, particularly toward the end, is plotting data and visualizing data. So here's an example of some data, and it's not really that exciting to look at. This is temperature anomaly data for, I don't know exactly what the time period is here, but this is showing us difference in temperature from one year to the next, or something like that. It actually doesn't look like temperature data because it's got minus 123. But anyway, if you start out with something like this in a text file and showed this to someone, it's not going to have very much impact with them, other than maybe they're going to immediately stop listening to you because they're just going to glaze over and say, what do I even, where do I begin to kind of get something out of this? But this is a typical kind of format of the data that you would want to visualize. And it's not that interesting. if we take this same data file and consider some other type of plot, one possibility is to do something like an XY plot here, where now you get a much higher impact visual of what this data set is showing. So this here would be, for example, on the vertical axis showing the temperature anomaly. So if you have some period of time, in this case, calculate the average temperature between 1901 and 2000, and then just go along and say, for each month, what is the difference in temperature between that average and this month? You start to see something like a warming trend here in the data, and this is probably not something that's that surprising to people that are at a university, that the climate has been warming over the past past 150 years or something like that. And in some cases that warming is quite clear. This has a much more obvious and sort of simpler message when you look at this kind of plot showing how temperature varies over time. We could take this same data. This is just global mean temperatures. So this is showing, for the entire planet, giving us much more obvious indication of the warming, particularly from 1970 onward. But we could consider plotting the same data in another form. So in each case, we're working with a similar type of data file, now showing temperature anomaly data over a similar time period. This is for 1 month because we don't have a time series plot here. So this is March of 2016 with a 30-year reference period for the temperature average, but now showing it on a map. And so you can see what parts of the Earth are warmer than average during that time period. And you can begin to see kind of how certain places in northerly latitudes are warming more than other places. Of course, this is just for 1 month, and so you might want to consider something that includes not only this kind of spatial data, this map view, but also time in the same plot. But I think you can agree that both of these visualizations, whether it's a time series or whether it's something like this, are much more intuitive than looking at the data file itself. So the message here, I think, is fairly clear. And if we look at a recent nice example of how to include both space and time in temperature visualizations, perhaps some of you have seen this little video. I don't know whether has anybody seen this yet? Yeah, a handful of people. So there's this guy, Antti Lipponen, at the Finnish Meteorological Institute, who in his spare time likes to make visualizations of temperature data. And he had one that came out last summer.
It's actually maybe a couple of weeks ago.
Well, this was a couple of weeks ago, but the year before, he published something that was like this sort of circular plot with these little bars that would kind of extend and shrink as showing how temperature varied for a number of different places in the world. And it got quite a bit of media coverage because it was a really intuitive way to look at this temperature data, and it had a high impact. And that's, when you start dealing with your data, one of the things you want to be able to convey is the importance of the data that you're looking at. So we'll take a look here at this visualization. In this case, I think it's fairly intuitive, but you probably can't read. Maybe you can, that's not too bad. You can probably read the country names. So each one of these little circles is going to correspond to some country, and we're going to go from 1880 until 2017 and look at how temperature varies in terms of temperature anomalies for each one of those years. And so what you can see as this thing plays is that the red dots are going to show us temperatures that are warmer than average, blue would be cooler than average, and I think at least at the beginning, you don't necessarily see a clear trend, but as the time advances, you should start to see something rather striking. So the message here, I think, is relatively clear by this stage. There's a lot more red on this plot than there was at the beginning. And here we now have spatial data and time mixed together in a nice and I think fairly intuitive visualization. The reason we choose to use this as a motivation is because I think this is also, well, I guess I shouldn't say we think this is also something that is intrinsically appealing to both the geologists and geographers. To deal with spatial and time data with something like climate is a kind of common ground for, I think, for many of us. And that's the type of data that we're going to end up working with in most of the course for the exercises, is this kind of climate data, because there's a spatial component to it that maybe the geographers will have an interest in, and many of the geologists are also interested in how climate changes over time, perhaps longer time scales than the last 120 years, but
basically after this 7 weeks, so last year we had this ambition to actually do a similar kind of thing, and we actually did it. So let's see how this year we can do, but the idea is that after the 7 weeks you should actually be able to do something like this.
Yeah.
It didn't turn out exactly like that, but still the idea is the same.
Yeah, perhaps wasn't quite as nice looking, but
Yeah.
But the point is that this is done in Python, and the Python code and the way in which this was done, I believe you can find the original source code for making this plot online, and at least that was the case for last year's version of this. And we're going to teach you how to use more or less the same plotting
Principles.
Yeah, same plotting principle, same plotting library for Python, so that maybe you won't make one that looks quite this nice, but we'll see what we can do in 7 weeks. But this will give you an idea of kind of how far you can go in 7 weeks, that you could even think that you could make this kind of visualization in a relatively short amount of time. So, yeah, and you're welcome to kind of go back and take a look here at any of the data if you'd like. For the moment, I think we'll move on here to a bit of basic stuff about computing. So before we can get into doing anything in Python, I told you that this wasn't really going to be the kind of typical computer scientist introduction to programming, and it won't be, but we do have to know a few things about basic ideas, even simple questions like what is a computer? Well, I think probably you all have some idea about that, but we can perhaps define that a little bit.
We can also ask about.
Yeah, so we'll come to that in just a moment. But for the moment, we're going to start here with just giving a general overview of some common computing practices, talk about what computers and programming languages are, and then talk about some of the components of a computer program, just to give us an introduction to where we're headed before we get into doing any of the Python programming language. And one thing we like to emphasize at this point is that neither one of us are computer scientists. I think Volko is also not a computer scientist, and we're all self-taught and I would say somewhat capable programmers by this stage. And there, I think, is kind of a growing need to know how to program as a young scientist. As someone who's studying science, I think that learning to program is essentially part of your basic education at this stage. I don't think that everywhere that bachelor students are learning how to program, so you're still kind of setting yourself apart a little bit from the crowd, but it's really become kind of a fundamental piece of knowing how to be a scientist, is having a little bit of basic programming knowledge.
Yeah, exactly. And in Finland they start to teach kids to program on the 3rd grade, so it's actually about time for us as well to learn some programming.
So you've got about 15 years where you can put programming on your resume and have that mean something. But yeah, so we've learned in many cases the hard way, and we're hoping to share with you a little bit of how to learn things in a slightly easier way, to learn things the right way, because I've had to break bad habits of my own from learning how to program, and we just want to get to the stage that we're functional. You may not be a superstar by the end of the course, but maybe you could feel good about just writing some simple programs to read in a data file and make a plot. And that's a starting point where we hope that you'll then be able to build as you go on and get more experience. In terms of why you want to know, well, I think I could certainly speak for geology and say that it's becoming more and more quantitative, that the time when you could just go out and observe things and describe landscapes, describe geological features, is sort of fading. And now there's a need more and more to sort of understand processes, to bring in some kind of simple model to relate to geological observations, and I think probably exactly the same thing is going on.
It's the same thing going on in geography, so it's more and more there are needs to actually be able to process more and more data. It's becoming like a fuel for research and try to understand our environment. Of course, there's always a need to have like qualitative research as well, but indeed the trend is towards the quantitative stuff.
Yeah. So this is now basically a fundamental part of both of these fields of science, and so of course that's going to be a skill you need to be a better scientist. In addition, programming gives you the kind of a Swiss Army knife, in a sense, that it allows you to solve a lot of problems with one skill, and it makes you very flexible in a sense that if you have a piece of software that can do something, but it doesn't do what you want, you have the potential to be able to write your own program to do what you want. If you want to be able to analyze data in a certain way, produce a plot in a certain form, and Excel won't do it, well, chances are that you can figure out a way to do it using Python, and it's more than likely not that difficult. Or you can go on Google and find an example of someone else who's done the same thing and borrow their Python code. But in terms of being flexible, it's also that there are many different software packages now, like ArcGIS, that include the possibility to directly link in Python programs that you've written. So I think the software designers have realized that they can design things around the main stuff you want to do in Arc. Of course, you should be able to plot shape files, and you should be able to load raster data sets and blah, blah, blah. But if you want to do something like more sophisticated calculations based on the data, maybe you have to bring in your own little Python code.
Also, one thing that has really kind of taken Python as popular as it is nowadays is the kind of huge boost in machine learning and artificial intelligence, which is actually driven by Python coders and Python programs. So that's also like if you know these principles and at some point become interested for some machine learning stuff, it's actually a pretty good skill to have at this point.
Yeah. So this is just a simple example of, I don't know what version of ArcGIS. I should probably update this with something more recent.
Yeah, we have quantum GIS.
Yeah, okay, all right, yeah. So anyway, you can see here that there's the little Python interpreter window that you can launch directly from within Arc. And Quantum GIS, I think, is even better in terms of Python integration because it's written, if I'm not mistaken, in, or a significant part of it, I think, is written in Python. Yeah. And it uses a lot of the Python geospatial libraries in Quantum GIS. And I don't know, maybe this will be a bit of a hard sell, but programming actually is pretty fun. And it doesn't involve, in many cases, logic that's that complex. It's not to say you can't make a really complicated program, but in most cases, solving problems using a simple program involves stripping it down to the essential parts and thinking of the basic logic that you need to solve the problem. For people, at least like myself, I find that to be something that's kind of a fun challenge. And I think this is the reason why, like Henrik, you mentioned, that kids are being introduced to programming and relatively young now, is because it's also fun for them to think of ways to like put the steps together in the right order to get some cat to like find the cheese at the end of the maze or whatever. I mean, they have these very simple.
Yeah, they are not doing like similar programming as we are doing, but they basically learn the principles and the kind of logic behind, which is of course already like half of the things that you understand how things work.
Yeah. So we'll see how you come out at the end after 7 weeks, whether you think programming is fun or not. But I think that the majority of the students actually in years past have found it to be maybe more fun than they expected. I think I'll keep it sort of neutral. Now, in terms of the ways that we can make ourselves better scientists in terms of programming, this is the scientific method. I suppose that at least some of you are familiar with this kind of general concept of how science is intended to be conducted, where you have your question that you're going to answer and you get some information, create a hypothesis, and then come up with an experiment that will test that hypothesis, look at the data, blah, blah, blah. Perhaps you've at least seen some version of this scientific method. The things that can help in terms of programming and where programming can help us, at least at the moment, I wouldn't say it can help us in defining a question, although in some sense there is.
You might get some interesting kind of hints, maybe to kind of go to a certain direction, but not maybe that much.
Yeah, but the main things that that are basic, fundamental parts of where programming can help us is gathering information and resources, allowing us to sort of assimilate data and collect large numbers of observations, testing hypotheses, performing experiments. Of course, if you want to do some kind of data analysis, if you want to run some sort of numerical model, you can write programs that will do that and allow you to do experiments that you couldn't do in other ways. Analyzing the data, of course, is a big part of the data science part of what happens using the Python programming language, and interpretation as well. So how you visualize your data, how you take the raw output and sort of come up with the conclusions that are useful are things that basic and simple programs can help with. And if we learn how to program in the kind of good way, in the way that computer scientists would like to see natural scientists learning to program, we can do things like make our analysis reproducible, make the testing of the hypothesis something where you can say, okay, hey, you don't think my results are right? Here's my code, you can run it, and you can reproduce the results yourself. And that's a very nice thing, as well as retesting. So, allowing other scientists to confirm your results is something that whenever there's a kind of big breakthrough, there's like half the scientific community is like, whoa, what a cool thing. And then there's the other half that's like, what did this guy do to get this result? That seems suspicious.
And also, in addition to, come on. Yeah, so in addition to just retesting, so it's also about if you kind of share things openly, which is basically what we really kind of support and emphasize that people should do that, especially in science. So also that if you share the things and if other people actually get excited about the things that you have done, so it's not only on your shoulders actually developing that thing further, but you can actually kind of gather around a collaborative network that actually helps you to develop things further.
Yeah. So I think we've made a case that's I think fairly strong at this point of why learning basic programming is important. Probably you were already like, yes, of course, I know I should learn this, and we can stop hammering that point at this stage and go back to something that's a little bit more interactive and ask you a question about what is a computer. And in this case, we have a poll again. So if you can go back to the polling page, it's down here, this Geo-Python .github.io/poll. Do I have, yeah, here we go. There's the URL as well. You can put in your own thoughts about what a computer is, and you can also support the things that other people have suggested. So you can vote for the options and you can add options. We're testing out all the different polling possibilities this morning. And I'll see if I can maybe switch over for a second here to the output for here. So computer emoji is winning.
Okay, we have a winner.
But already, as we're looking at the responses coming in, there's key things that are sort of ascending to the top beyond the nice emoji. That a computer's a machine, problem solver, a tool, these kind of things. And I think to all of us, a computer is defined a little bit differently. In terms of the formal definition, we can come to that in just a second here. We can maybe watch for a few more suggestions here. I see a fancy calculator. That's
everyday assistant. That's nice.
Yeah. I'm actually surprised that does what you want is on there. We'll see whether the computer does what you want when you start learning to program. But yeah, I mean, there's a lot of different elements here about the fact that the computer is some type of piece of equipment that can be used to solve problems as a tool, and yeah, there's lots of good ideas here. If we ask the computer scientists what a computer is, they would draw a picture like this, so not quite the same as the little computer emoji. And in this case, here it is. It's a machine. And it's a machine that stores and manipulates information under the control of a changeable program. So there were a few responses that mentioned like hardware and software, or somehow included program in there. The program itself is not really part of the computer, but it controls what the computer does. The computer basically processes information, and if we took it down and said, let's strip it down to its essential elements, there's some kind of input device, which could be a keyboard, mouse, microphone, whatever. There's a processor in there, and there's memory where information that's being processed is stored, and there's output devices like a screen or speakers or printer or whatever. And secondary memory in this case would be like a hard drive, so someplace where you're able to store information. Those are the essential elements of what the computer is. It manipulates information, so in a sense, while the computer can just return to you what you type into it or what you give it, it normally will process that information in some way, so that if you use your microphone to tell it to load some YouTube video, it will interpret that and then load that YouTube video you want to watch. We hopefully will output it in something that's not bits and bytes and something that's hard to interpret, but something that's easier for humans to understand. The other important part here is that it is controlled by a changeable program. So if we think about that, anybody who has a smartphone, this is a computer by this definition. It has all the elements of what a computer is. If you happen, I don't think anyone's walking around with a calculator in their pocket, but if you had a calculator in your pocket, a calculator is not meeting the definition of what a computer is, unless it's a kind of programmable graphing calculator. But a normal calculator can only do what its chip is kind of permanently programmed to do. You cannot change the calculations that are done inside a calculator because it's hardwired to do certain things like add, subtract, divide. So the changeable program part is an important element here, and that's what we're going to be focusing on, is changing programs in many cases and creating programs to control what the computer does. In terms of what a computer is good at, this is probably the simplest definition, which is a well-defined, clear task. If you can communicate to the computer something simple that it should do, computers are very good at doing those type of things. So if you said and knew how to talk to the computer and tell it to add 2 plus 2 and return the answer, you might type something like this in Python. So this is just a kind of simple example of printing 2 plus 2. And of course, when you hit enter, tell the computer to do its calculation, it writes out that that value is 4. Now, computers are also good at things like storing data and manipulating data. Repetitive calculations is a big part of what many programs end up doing. Load in different data, but do the same calculation over and over. That's the kind of thing that once you have a good working program, the computer is very efficient in terms of repeating the calculations and processing instructions or other data. And in this case, just to show you what's going on, this would be an example of what the prompt would look like if you're typing something into Python. This is a function called print. It's probably quite obvious what it does, and then the value that it returns is the number 4 there. Now, computers aren't so good at abstract tasks, or at least maybe they're getting better at dealing with abstract tasks. But if you don't tell the computer how to do something, generally speaking, it won't work well for you. So you might say, hey, calculate the value of pi for me, computer. And if you don't give it a program that tells it how to calculate the value of pi, it won't be able to do that. And even if you could probably have the same experience with your phone. I've got an iPhone, and there's like this Siri lady in the phone. If I ask Siri to do things she doesn't understand, she just says, I don't know how to do that. So like if I say, where are my keys or something like that, Siri doesn't know where my keys are. And so that's a task that the software is not programmed to be able to do. Now if I ask, where's the closest grocery store, all of a sudden it knows, oh, I know how to find that. So if you can't define the task well, then the computer won't struggle. Of course, a computer is something that is very good at calculating the values of pi. So this is the first 1,000 digits of pi calculated by a computer probably in a fraction of a second. And in this case, all we need is a piece of software that tells it how exactly it's meant to do this calculation, and then all of a sudden it's like that. Computers also aren't very good at doing things that require too much computing power. So if you want to calculate the change in temperature in the Helsinki region from 1900 to 2017 with a 1 meter resolution, chances are that calculation is going to be too big for the computer to handle. There's too much information to be processed, and even if you use one of these supercomputers from the CSC, for instance, this is the SISU supercomputer. You can see here it's got 40,000 processor cores. So my laptop has 4. So if I had 10,000 on my laptop, that would be not quite the same power as SISU. It's a big computer, and it's got a lot of power, but it still can't do everything. So you can make programs that are just too demanding even for the biggest computers to be able to calculate.
Yeah, this is kind of where the baseline kind of shifts all the time, because the computers are getting more and more powerful at all times. So they are getting better, but there's always a new problem that is bigger than the ones that we want to solve. So that's kind of the reality.
Yeah. So we can certainly come up with things that the computers can't handle. Now, I mentioned that computers are managed or controlled by the programs that they run, and so we can talk just a little bit about what a program is. And here's a couple examples just to get you thinking. This is some Python source code down here at the bottom, and you don't need to really understand what this is doing, but this is just defining some variables, and you'll get some experience even with defining variables later on today in the course. And this is the kind of old school Fortran punch cards. So I don't quite come from this era of programming, but back in time, you used to manually punch your programs into a piece of paper or a stack of little pieces of punch cards and feed them into the computer, and that's how it ran programs. I'm quite grateful that we don't have to do that anymore. But in terms of the basic story of what the program is it's our detailed list of what the computer should do. Step by step, exactly what the computer should calculate. And so in this case, if you look at the Python source code example, each line has a specific calculation that should be done by the computer, and they need to be done in that order in order for the program to work. The program is something that we can change, we can edit the software, and when we run the program, it's going to change what the computer calculates and what it outputs. And if you want to use the word software, that's basically more or less the same idea as what a program is. You might not think that your little 5-line Python script is a piece of software, but it's just as much software as the operating system for Windows or whatever. The language is the way that we talk to the computer, and so it's in many ways not that different from spoken languages between people. We have to have some way as humans to interact with what the computer understands, which ultimately comes down to bits and bytes. It's not so intuitive for us to speak that language, so we have these programming languages as a way to go between what humans understand and what the computer understands. They don't yet understand our native languages, although, again, I can ask Siri to do a handful of things, and she knows how to do that.
And programming languages are also in that way similar to spoken languages, that there are certain like programming languages that are closer to each other. For example, like thinking of Finnish and an Estonian language, so that they are quite similar. For example, like Python, and I don't know what would be similar to that one, but like Julia, for example. Yeah. So kind of, yeah.
Yeah, and in terms of what the language needs to do, if we're going to give the computer instructions that have to be specific, the language has to be exact and unambiguous, meaning that there's no uncertainty when you tell the program to print something. The computer doesn't go like, oh, should I do this or that? It knows print means exactly to do one thing. And in terms of the way that it operates, we have the form of the language, the syntax, and so you'll be probably struggling with the syntax in Python for a little while as you learn the basics, and then the meaning of what that syntax is. So in this case, syntax might be something like the print statement, print, parentheses, something, parentheses. That's the syntax, and its meaning is display something on the screen. And of course, Python's just one of many programming languages. We saw already that you have some experience with others. So in Python, if we want to go back to the classic hello world example of how to print hello world with the computer, this is how you would do it in Python. Just the print statement, parentheses, hello world in quotation marks, and then your close parentheses. And I don't think we really need to ask you what's going to happen here because hello world is going to be written to the screen. I think we can understand this bit of the program. And again, the syntax here is the print function, and the meaning is to put something on the screen. What would happen if we tried to pring hello world instead of print hello world? Do you have any idea? Nothing? Yeah. So what you're going to get in this case is some kind of syntax error that says, wait, I don't know what pring means. And of course, Python will have its own way of telling you. I think in this case, I don't know exactly what type of error would be raised, but you're going to get something that says, pring is not something I understand what to do. If we go back here, for those who've dealt with MATLAB, print is the same as using disp in MATLAB, so display, and then looks quite similar. If you've done Fortran, you would do the same thing here in a simple program to write hello world, and in C, things look a little bit more complicated, but each one of these programs would write the same thing to the screen. It would print hello world when you run the program. And these are all kind of high-level programming languages. These are not directly understood by the computer. There's something that actually interprets what we've typed in and then converts it to a language the computer understands. But fortunately, we don't need to know anything about that part. The computer scientists can worry about that stuff. Okay, so let's just talk for a moment here about developing programs, and I think we're going to be coming up to maybe having a coffee break here in not too long. But here's a basic strategy when it comes to writing a program. You might have in your mind that like, oh, I'm going to learn how to program in Python, so next time I want to do something, I'm going to sit down and start coding. That's one possibility, but I think both Henrique and myself would probably advise you that that's not the wisest way to start doing your program, but rather there's a bit of thought that goes into things before you even start writing the Python code that you want to use. And we'll go through that now with just a simple example. These are some of the steps that you want to go through. And implementing the design, step 4, so halfway through this set of steps is where you actually start typing things in Python, for instance. And then you run your code and see whether it works, and then go through debugging. And if you need to, you can then maintain it. But you can see at least half of the process is not related to anything in terms of writing code itself. So I'll make fun of myself for a moment as an American, and since I learned temperatures in Fahrenheit when I was growing up, I might struggle living in a country where they don't use Fahrenheit to measure temperature. So for those who don't know anything about Fahrenheit, 70 degrees is nice, 90 degrees is hot, and water freezes at 32. It's very intuitive. Here, of course, we don't use Fahrenheit, and so if I want to know what clothing I should put on in the morning when I go out to go to work, I need to figure out what the temperature is in Fahrenheit based on a weather report that might tell me a temperature in Celsius. And I think I can write a little program that will help with this. So the first step here is this: analyze the problem. Before we can even get anywhere near writing out a solution in terms of software, I have to think about what it is that I actually want to know. And in this case, I think the problem is relatively simple. I don't know what the temperature in Celsius means in terms of what clothing I should put on. Now, the specifications of this program, or what I'm going to end up writing, will be, what kind of information do I need to know in order to be able to figure out what the temperature is in Fahrenheit. So I need to describe what this program is going to do. I don't need to worry about how it's going to work, but I need to have something in mind like, well, the program should let me type in a temperature in Celsius and it should give me back a temperature in Fahrenheit. And then I can go, oh, now I know what to wear. And these are kind of the input and output values and how they should interact in the program, not in detail, but just in general. So at this point, I kind of have a bit of a picture of what's going on, and I can move to step 3, which is the design of the program. Here, you remember that the computer needs to process instructions step by step. This is the point where we can write down step by step what the computer should do. Not in its language, not in a programming language yet, but just in some language that we understand. English, Finnish, whatever language you like. But now we can go, first, step 1, read in the temperature in Celsius. Step 2, calculate the temperature in Fahrenheit based on the input temperature in Celsius. Step 3, return or print the temperature in Fahrenheit to the screen. So, fairly simple program. If I write down those 3 steps, I pretty much know at that stage what I need to do, what the order of operations should be, and now I'm at the point where, okay, now I can convert this basic template of the set of instructions into something in Python. And writing this pseudocode is something that we really would encourage you to think about when you start working on some of the exercises. If you have to write some little piece of code, you'll save yourself a lot of time if you just think through it before you ever start typing things in Python and say, what are the steps I need to do?
And of course, this is kind of a thing that while you're kind of getting better in programming, so for example, this kind of thing where we convert temperature to another. So when you are kind of knowing what you do, you probably don't actually describe all the steps like this kind of a simple function in the program. But for example, if you have a bigger program that does lots of stuff, so have the basic things like steps that are actually included in the program. So that is at least what I assume you do as well, but I do. So I write those down in the code always.
No. So you'll save yourself a lot of time and a lot of headaches if you can get into the habit of thinking through the steps one by one. First, once you have that kind of written down set of instructions, if you've learned a little bit of the Python language, it's really easy then at that stage to convert that set of instructions to something in Python. And at this stage, when you don't know much of the Python syntax, it's going to be a little bit more challenging. But most of the time when we have problems that take a lot of thought in terms of programming, it's often because the script or the set of instructions isn't that clear, and you spend a lot of time just kind of stuck trying to figure out what to do. So here we're just going to convert the pseudocode to the equivalent in Python. At that stage, we can then test the program. So I can run the piece of software that I've written and see whether it works. I can put in some test cases maybe. So if I know that water freezes at 32 degrees Fahrenheit, and I know it also freezes at 0 degrees Celsius, I could put 0 degrees in for the temperature in Celsius, and my program should tell me that's 32 degrees Fahrenheit. If I know the temperature of water boiling in Celsius is 100 degrees, my program should tell me that that's 212 degrees Fahrenheit. So we can check to see whether that's whether the program returns values that we know it should. And after that, then if someone finds my program and asks for some additional features, like to put the temperature out in kelvins or something like that, because they're used to kelvins for whatever reason, then I might have the responsibility to maintain the program. In this case, probably that's not likely to happen, but for some other things, if you write some little useful script for processing data for your master's thesis, and then there might be a chance that your thesis supervisor asks you later on to say, like, hey, could you add this thing, or send me the program and tell me how it works, or whatever. Okay, so that's the kind of basic stuff on what a computer is, and I'm not going to make you suffer through answering questions at this stage, but we talked about what a computer is, and I think our essential definition was that it's a machine that processes information under the direction of a changeable program. The program itself is just a list of step-by-step instructions for what the computer should do, and it's going to be written in some programming language that's an exact thing telling it precisely what to do. And then we've just seen the steps about developing the program, and that about half of the time is thought before you ever start writing any of the software. And if you think about things ahead of time, your life will be a lot easier.